Needless to say, that huge amount of rotational kinetic energy must be stored in planets and in stars. And I would like to spend quite some time on that. It's a very interesting subject. I will first discuss with you the sun and the Earth and see how much rotational kinetic energy is stored in the Earth and in the sun. This is also on the 801 homepage, so don't copy this. Let's first look at the sun. We have the mass of the sun. We have the radius of the sun. So you can calculate the moment of inertia of the sun. I have used my 2/5 mr squared, which is really a crude approximation, because the 2/5 mr squared for a solid sphere only holds if the mass is uniformly distributed throughout that sphere. With a star, that's not the case, not with the Earth either, because the density is higher at the center. But this sort of gives you a crude idea. So you have there the moment of inertia, which is easy to calculate with that 2/5 mr squared, and I did the same for the Earth. This is the radius of the Earth, and you see the moment of inertia of the Earth. Now I want to know how much kinetic energy of rotation these objects have. Well, the sun rotates about its axis in 26 days, the Earth in 1 day, and so I finally convert everything to MKS units, and I find these numbers for the rotational kinetic energy. Now look at the number of the sun. 1.5 times 10 to the 36 joules. Our great-grandfathers must have been puzzled about where the solar energy came from, the heat and the light, where it came from. And conceivably, it came from rotation. Maybe the sun is spinning down, is slowing down, and maybe the energy that we get is nothing but rotational kinetic energy. If that were the case, however, since the sun produces 4 times 10 to the 26 watts, 4 times 26 joules per second, it would only last 125 years. So you can completely forget the idea that the energy from the sun, that we now know, of course, is nuclear, but our great-grandparents didn't know that the energy would be tapped from kinetic energy of rotation. Let's look at the Earth. 2.5 times 10 to the 29 joules. Well, let me try some fantasy on you, some crazy, some ridiculous idea. And I'm telling you first, it is ridiculous. Remember that the world consumption, the 6 billion people on Earth, consume about 4 times 10 to the 20 joules every year. So if somehow I thought if you could tap the rotational energy of the Earth by slowing the Earth down, maybe we could use it to satisfy the world energy consumption. I wouldn't know how to do it, and it is, of course, complete fantasy. All you would have to do is slow the Earth down by about 2.4 seconds after 1 year. So you slow it down after 1 year, the day wouldn't last, day and night wouldn't last 24 hours, but only 2.4 seconds longer. But of course, after 1 billion years then you would have consumed up all the rotational kinetic energy, and then the Earth would no longer be rotating. It is, of course, a crazy idea, but sometimes it's cute to speculate about crazy ideas. There is an object which we call the Crab pulsar. It is a neutron star, and it is located in the Crab Nebula. The Crab Nebula is the result of a supernova explosion that went off in the year 1054. And during my next lecture, I will talk a lot more about that. For now, I just want to concentrate on this neutron star alone. And so here you have the data on the Crab pulsar. The mass of the Crab pulsar is not too different from that of the sun. It's about 1.5 times more. The radius is ridiculously small. It's only 10 kilometers. All that mass is compact in a 10-kilometer radius sphere. It has a horrendous density of 10 to the 14 grams per cubic centimeter. So, of course, the moment of inertia is extremely modest compared to the sun because the radius is so small. And the moment of inertia goes with the radius squared. However, if you look at rotational kinetic energy, the situation is very different because this neutron star rotates in 33 milliseconds about its axis. So it has a phenomenal angular velocity. And so if now you calculate 1/2 I omega squared, you get a fantastic amount of rotational kinetic energy. You get an amount which is more than 1,000,000 times more than you have in the sun. And this object, this pulsar in the Crab Nebula, is radiating copious amounts of X-rays, of gamma rays. There are jets coming out of ionized gas. And we are certain that all that energy that this object is producing comes from rotational kinetic energy. And I will give you convincing arguments why there is no doubt about that. If you take the Crab pulsar and you calculate how much energy comes out in X-rays and gamma rays and everything that you can observe in astronomy, then you find that it has a power, roughly, of about 6 times 10 to the 31 watts. It's a phenomenal amount if you compare that with the sun, by the way. The sun is only 4 times 10 to the 26 watts. So the Crab pulsar alone generates about 150,000 times more power than the sun. We know the period of the pulsar to a very high degree of accuracy. The period of rotation of the neutron star is 0.03350028583 seconds. That's what it is today. I called my radio astronomy friends yesterday and I asked them, what is the rotation period of the neutron star in the Crab Nebula? And this was the answer. Tomorrow, however, it is longer by 36.4 nanoseconds. So tomorrow, you have to add this. That means it's slowing down. The Crab pulsar is slowing down. That means omega is going down. That means 1/2 I omega squared is going down. And when you do your homework, which you should be able to do, to compare the rotational kinetic energy today with the rotational kinetic energy tomorrow, you will see that the loss of energy is 6 times 10 to the 31 joules per second, which is exactly the power that we record in terms of X-rays, gamma rays, and other forms of energy. So there's no question that in the case of this rotating neutron star, all the energy that it radiates is at the expense of rotational kinetic energy. It's a mind-boggling concept when you think of it. And if the neutron star in the Crab Nebula were to continue to lose rotational kinetic energy at exactly this rate, then it would come to a halt in about 1,000 years.